Hello everyone. So today let's discuss the Dinic algorithm. Previously we had discussed on the Edmonds-Karp algorithm, right? So today we'll be discussing on the Dinic algorithm for the maximum flow. This is also for the maximum flow. This one similar to the Edmonds-Karp as well as the this one Hopcroft, right? So let's see what the definition part say here. Let's see what the definition part states here. So Dinic's algorithm is an efficient method to compute the maximum flow, right? It's an efficient method to compute the maximum flow in a flow network. What it does, it builds a level graph. It builds a level graph using BFS, right? It builds a level graph using the BFS and then sends blocking flows using the DFS using no more augmenting paths, right? No more augmenting paths exist, right? Again, it builds a level graph. First, what it does, it builds a level graph using the BFS, using the breadth first search. Just remember this one. This is very important. And then sends the blocking flows using the DFS. So it uses both BFS and the DFS. And then sends the blocking flows using the DFS until no more augmenting paths exist, right? So this is the definition part. Now let's move on with the explanation part, man. Yeah, this is similar to the this one, man, Edmund's cup. Just listen to this carefully. So imagine we have a network of pipes, right? So network of pipes in the sense we'll be considering this one as basically these are the edges. We'll be considering having this one, a network of pipes, right? Connecting tanks, right? So imagine this one we have a network of pipes, nothing but the edges connecting the tanks, nothing but the nodes, right? Each pipe having a capacity, nothing but the maximum flow it can carry, right? The maximum amount of flow that it can carry, the each pipe can carry, right? So our goal is to push as much flow as possible from the source to the sink, source S to the sink T, right? What is our main goal? Our main goal is to push as much flow as possible from the source S to the sink T without exceeding the pipe capacities. So pipe should not exceed its capacity without exceeding the pipe capacities. What is our goal again? Our goal is to push as much flow as possible from the source to the sink. Source nothing but will be considering S, T nothing but the sink. Don't get confused here when we make use of S and T, right? So without exceeding the pipe capacity. So this one we have to keep in mind. So Dinic's algorithm works in two phases, right? So one is so we'll be going with the BFS and the DFS phase, right? So BFS phase. So this is nothing but the level graph construction. So what we will do here, we will be finding the shortest distance, nothing but in the form of edges from S to all the reachable nodes. S nothing but the source. From the source to all the reachable nodes. For that, we'll be making use of the BFS, right? Level graph construction. Next phase is this one, DFS phase. Nothing but the blocking flow computation. For the blocking flow computation in the sense, we will be sending the flow only along those shortest paths until we can't send anymore. So this process repeats until no augmenting paths remain. No augmenting paths remain, right? Giving us the maximum flow, right? It repeats until no augmenting paths remain, right? Giving us the maximum flow. Let's try to implement the same thing, this one, whatever we have discussed now in the form of code or the algo using Python programming language, right? So first thing, so let's go with the DQ. Let's import the DQ. We need this one. So this will be handy basically from collections import. Let me go with DQ. Now, let's move on with the first step, nothing but we need edge class basically. We'll be going with the edge class just to store the capacity, flow, as well as the reverse edge, right? So I'll just go with here class edge. This is fine. Yeah. First, let's go with the initialization part, nothing but the init and Python, right? So I'll just give here init. 1 second. Yep. So let me remove this along with the self. We need parameters. This one, V also capacity. Yeah. Now within the constructor part, so I'll just go with self dot v equals v, right? So this is fine. The next part. So why this is taking actually I've given this one semicolon. Yeah, sorry. This one, let me go with capacity. This is not showing. Yeah, let me write this one entirely. So now this will show. Yeah, yep. Next, we have to initialize the flow as well. Initially, let's set this one to the 0. Also, we need rev. So I'll just go with the, so this one, nothing but the reverse one. Don't get confused, not the rev actually. Rev has different meaning. So rev is nothing but rev. We have considered this one, the this one reverse. We are just initializing the reverse, basically reverse edge pointer. You can call it as reverse edge pointer, right? So we are done with the initialization part. Now let's go with the main class, nothing but the Dinic. Dinic class, what it does, this is the graph class for the Dinic's algorithm, right? So I'll just go with class here. Let me call this one Dinic itself, as we are dealing with the Dinic's algorithm, right? Again, let's go with the initialization part here. So this is fine. Yeah, let me remove this one along with the self. I need n as well. Yeah, now let me go with self dot n equals n, and let me go with graph here. This is fine, I believe, for in range basically. Yep. Yeah, range of n. Let me pass n man here. This is fine. Yeah. Now let's do one thing. Let's move on with the next step, or the step 3 here. What we'll do here, we will add the edge. Nothing but when I say we'll add the edge, we'll be adding the edge. Also, we'll be reversing the edge for the residual graph, right? So let me go with the function added itself. This makes sense actually. It's relevant here, right? So let me go with self. We need edges u and v along with the capacity, right? Yep, simple one. Now let's add whatever the things that we need, man. I'll just go with the forward here. Forward equals, let me call edge. So this one has to be v along with the capacity. Next thing is, let me go with backward here. Backward. So this one edge. So this is fine. Let me go with u comma 0. This is also fine. Next, let's go with a forward dot reverse actually. Yeah, I'll just go with the rev equals, let me assign this one to the backward. Also, we need backward dot reverse, right? So this one for the rev. Let me assign this one to the forward. Yeah. Now we're left with only two things. I'll just go with graph of u. So we have to append this one to the this one forward, right? So we have to append the forward to the this one u basically. Graph in simple terms. So I'll just do the same thing. Self dot graph of, instead of u, I'll just go with a v. V, we have to append this one to the backward instead of the forward. That's the only difference. Yeah. Now we are done with this part, man. Let's do one thing. Let's go with the next step, nothing but let's go with a BFS that builds the level graph. So I'll just go with a dev BFS. This is fine. Self comma s, this one e comma level actually. Yeah. Now within the BFS function, let me go with the queue and let me assign this one to the DQ. So we have made use of the DQ, right? Same thing for making use of the this one. So I'll just pass S here. This is fine. So I'll just, we are making use of the BFS, right? So I'll just go with the level of S initially 0. This is fine. And standard BFS loop here, while of Q, while of Q. Why this is showing error here? Oh, I have mentioned entire queue here. Yep. So let's go with the queue. This is fine, man. Yeah. Now let's assign u to pop left. We have to pop, right? So this one has to be q dot pop left actually. This is fine. Yeah. Now let's go with the for loop, man. For e in self dot graph. This is fine. Self dot graph of u. Now if let me go with the level e dot v. If it is less than 0 and e dot flow, if it is less than e dot capacity, why this is not showing here? Is something wrong? So what I have written here, level this one v we are considering, so this is fine, less than 0, and we are considering flow less than capacity, right? So I'll type this one instead. Yeah, this is fine, I believe. Next I'll just go with the level of this one v. Let me go with level u plus 1. Yeah, now let me append this one v actually, right, to the queue. I'll just go with append. So I'll just append the v. This is fine. Now let's do one thing. We have to return what we need to return here, a level of t, right? So I believe we have to return level of v, or not the level of v actually. T we have considered, right? T go with greater than or equal to 0. So this is fine, man. Next, let's do one thing. Let's go with the function DFS. So we are successful in the BFS actually. We have to go with a DFS function as well as we have to go with a max flow function. These two things, right? DFS function because DFS sends the maximum flow through the level graph, right? So this one, just give me a second here. Yeah, I'll just go with def here. DFS. So let me go with self u comma t. Let me go with flow. This is fine. Level comma start. Yeah. Now, so within the DFS, if u equals t, then let me return. This is fine. I'll just go with the flow actually. Yeah, this is fine. Now let's do one thing. I'll just go with a while loop. So while, let me go with start here. While start of u, this is fine, is less than length of dot graph. This is also fine of u. Yeah, now this is fine, man. Yep. So within the while loop, let me assign e to this one graph. Uh, graph of u. This is fine. Start of u actually. Yeah. So this one has to be actually. Let me include one more. This one here. Close this one. Yeah. This is fine, man. Yeah. This is fine. So what if the level of this one v is equivalent to the u plus 1, right? So this one I can just write it in this way. If level, what is this one, vertex, if it is equal to level u plus 1, and also flow, if it is less than, flow is less than capacity actually. This is not showing, bro. What's the problem? I don't know. It's fine. So in that case, we have to go with a sorry, not continue, man. So I'll just go with the keyword current flow here. Segregate this one with the underscore so that this looks good. So this one will be min of, let me go with flow. Also along with the flow, what are the things? We have to go with the capacity as well. So I'll just go with the capacity. Capacity minus this one flow actually. Yeah, this is fine, man. Now after that, let me go with a variable name pushed actually here. Let me call the DFS. We are recursing here. So I'll just go with V as well as current flow. Let me consider this also level and start, right? Level and start. So this is fine. Yeah. What if pushed is greater than 0, right? What if pushed is greater than 0? So this one will be flow equals flow plus pushed, right? So this is fine. Also, mm, flow equals reverse dot flow minus pushed we have to go with, right? So this one I can write it in this way. Yeah, this is fine as well. Finally, we have to return pushed actually. Return pushed along with a, so we have to go with a start. So this one, let me go with start equals start plus one. Start of u, right? Edge u equals start of u plus one as we are performing DFS, right? So starting point. So next we have to return zero. Let's do one thing. Yeah, let's return zero here. Yeah. So we are done with this. Basically, we are done with the DFS part as well, right? So we are performing DFS, or we went with a DFS that sends flow through the level graph, right? So accordingly with what we discussed in the explanation. Now, we are left with only one step, nothing but one function. Here, let's go with the main function to calculate the maximum flow, right? So I'll just name this function max flow itself, as we need to calculate max flow. So this is fine. Let me go with self along with SNT. Yeah. Now let me initialize total to 0. Go with a standard loop. So this one, while of true, what we need to do, then well, let's assign the level to. So this one, minus 1 into n. Yeah, this is fine. If not, then let's perform BFS here. Then let's perform BFS here. We have to pass S T as well as level, right? So this is fine. Yeah. So the next step, we need to break actually. So I forgot this one. I think what do we call colon actually. Yeah. Now this works. Yep. Let me. We have to break out. Everything works properly. Yep. This is fine, man. Next, let's initialize start actually. Variable start to 0 into n. Yep. This is fine. What happened to this one? Oh yeah, we are going with a class, right? Have to go with the self actually. We are dealing within the class actually. Yeah, self dot n it has to be. Yeah, this is fine. Now let's go with a while true. This is fine as well. Let me go with flow equals DFS. So we'll be making use of the DFS and BFS both with the main function. Yeah, it uses basically the algo itself uses BFS and DFS, right? So we have already written the helper methods for BFS and DFS outside, so we can just make use of it within the main function max flow, right? So now let's go with the DFS man. What are the parameters that we need to pass here? S, T. Along with it, we have to go with the float. Float. Let me give here this part infinity man. Yeah, this is fine. Absolutely fine. Now let me pass the level as well. Along with the level, let me pass start. Right. So this is fine. Now, what if flow is zero? What if the value of the flow is zero actually? If it is equivalent to zero, then let's do one thing. Let's break. Right. So this is fine. The next part is total is equivalent to the total plus flow. Yeah. Now I can just go with total equals total plus flow. Yeah. The final one is I think we need to we are going with the total itself, right? So let's return the total. Let's return total. Yeah, we are done with the this one algorithm basically, right? Yeah, I have explained you this one step by step. Yeah, let's consider the example usage as well. So let me take that one from the Google man. Just give me a second here. So let me paste it over here. So n is 6 is number of nodes is 6 here. We are calling the Dinic, this one class Dinic here. We are passing n basically, n nothing but 6 for the example sake. We are considered 6. So 0 to 5 actually. We are starting from the 0, node 0, 0 to 5, 0, 1, 2, 3, 4, 5. So 6 nodes we are considering. So this is the bit actually, right? So this is fine. Values basically for the edge, right? So we have to determine the maximum flow itself, right? So denote maximum flow from 0 to 5 we have given, right? So before running the code, let me explain what we have done here so that we don't forget the things, man. Yeah. First, I'll just explain this one, explain this one very briefly, man. Just listen to this. This one edge class. This stores the destination, capacity, and the reverse edge, right? So this is needed for the residual network, right? So next, what we have written, Dinic class. So this Dinic class, this contains all the edges and main algorithmic functions. So within this itself, we are writing everything, right? So this is fine. Added, we have made use of the added helper method or the function here. So this adds forward and backward edges for the each connection. This is fine. Next, we have went with the BFS. What does the BFS function or the helper method do? It creates the level graph, assigning the levels based on the shortest distance from the source. This is fine. Next, let's move on with the DFS. DFS, what does DFS do? We know this. It sends as much flow as possible through valid paths in the level graph. So yeah, so now the max flow, the last one. So we are repeatedly building the level graph and level graphs actually, and sending the blocking flows until no paths exist. No path exists basically within the max flow. That's what we are doing within this particular function. This is main. Just listen to this carefully. We are repeatedly building the level graphs and we are sending this one blocking flows until no paths exist within the this one max flow function. So this is the main one. Yeah. Finally, the graph connections from this structure from source 0 to sink 5. So in the example, we have considered the same thing here, right? From 0 to 5 basically. Yeah. Finally, the graph connections form this structure, source 0 to sink 5. Basically, source we have considered 0 and sink we have considered 5. ST, right? So here, if you remember SNT, right? So the same thing. Where it went off. Our goal is to push as much as flow, this one, as much flow as possible from the source T, from the source S to sink T without exceeding the pipe capacity, right? Without exceeding the pipe capacity. Finally, the graph connections form this particular structure, source 0 to sink 5, and the algorithm computes the max flow. So what is the output that we need to get here? So maximum flow that we need to get here is 23. So I'll explain why we have to get 23, right? So here the maximum flow, we are printing this one for the interactive purpose, right? So here maximum flow we need to get here is 23. Why we have to get 23 here? See, algorithm finds multiple augmenting paths, right? So algorithm is written in such a way that it finds multiple augmenting paths. So let me give some paths like that, right? So it may be we can consider, see here, this is edge u v and this is the value between the edge, right? So n we have been given 6. So nodes we have here 0 1 2 3 4 5, total 6 nodes, right? So accordingly node n equals 6 we have considered. So edges, so these are the edges basically u and b, 0 1 0 2 1 2 2 1 1 3 3 2 2 4 4 3 3 5 and 4 5. These are the edges and this is the value basically, right? So this is fine. Listen to this. The algorithm finds multiple augmenting paths such as, so one path is, if you observe one path 0 1 3 and 5, right? So flow, if you consider the value, the flow will be 12, right? And another path if we consider, so this will be 0 2 4 as well as 5. 0 to this one 4 as well as 5. Flow here, flow is 11. You can just check accordingly with the example, right? So we have got 11 here. So no more augmenting paths remain here. So none of the augmenting paths remain here, right? So total flow we will be going with this path plus this path. We have to sum up, right? So this will be 12 plus 11, which leads to 23, which leads to 23, right? So the maximum possible flow from the source 0 to sink 5 is nothing but 23 units. We can just call this one as 23 units. So this is the output that we need to get. I hope this part is clear, man. Let me delete this one entirely. Now, see, now we have the understanding of the algorithm completely. Let me do one thing. Let me copy this one and let me come here. Let me give Control J. Yeah, let me hit clear screen here. Let me give Python followed by the file name.py, right? So we are having the error. What's the error here? Dinic.dfs missing one required positional argument start. So where is it actually? Line number 61. Number 60 .dfs we are going with, right? So this one DFS within the DFS. So just give me a second here. Line number 60. Where is it? are recursing here, right? So what mistake I have done here is in the line number 39, see, I have left the space here. So we shouldn't be leaving the space here. This is fine. And also here, as usual, in the line number 60, as it was screaming, so in the parameters, we haven't added the T at all here. So that is the reason we are getting the error. So this is fine, man. Now let me give Control J, give clear screen. Let me run the code. Yeah, now we are getting the maximum flow 23, right? This I have explained how we got 23. This is fine. Now we are done with the algorithm, right? So we are done with the algorithm. Let me do one thing. Let me summarize whatever we have learned so far, right? Just try to remember these 3 to 4 points, man, whatever I give. So first thing here would be Dinic's algorithm efficiently computes maximum flow using BFS, right? So it Dinic's algorithm efficiently computes maximum flow using BFS plus DFS, right? Using BFS plus DFS, right? So this one is fine. The second one is it's faster than Ford Fulkerson. So this one is faster than Ford Fulkerson and Edmonds curve, right? And also the previous algorithm that we have discussed, nothing but the Edmonds curve, right? Edmonds curve, especially for the dense graphs. It is faster than again Ford Fulkerson as well as the Edmund curve, especially for the dense graph. Just remember this one. This Dinic algo is uses PFS and DFS. This is fine to compute maximum flow. This we know. The second very important point is it is faster than Ford Fulkerson as well as the Edmund curve. This one Edmund's curve algorithm, especially for the dense graph, right? So the time complexity would lead to because of this one. So let me write it on this way. Because of V square E, right? So because of V square E in the worst case, but it performs much better in practice, right? So what is the key idea here? So we will build a level graph and then we will send the blocking flows, then repeat. Nothing but BFS and DFS, right? So then repeat. This is fine. Yeah. So this one because of V square plus E time complexity. Right? So this is fine, I believe. So this is it for the algo. These are some of the important points that I wanted to discuss. You have to keep this in mind, right? So now we are done with the what do you call Dinix algorithm. Next, we'll be discussing on the push relabel algorithm, right? So for now, this is it. Thanks for watching, guys.